I'm Anna Trombeva-Gavriloska, an associated professor at the Faculty of Architecture at the University St. Cyril and Methodius in Skopje. The title of this webinar is Contemporary Methods for Reconstruction of Reinforced Concrete Structures. The issue of upgrading the existing civil engineering infrastructure has been one of great importance for over a decade. Deterioration of bridge decks, beams, girders and columns buildings may be attributed to aging, environmentally induced degradation, poor initial design or construction, lack of maintenance and to accidental events such as earthquakes. The infrastructure's increasing decay is frequently combined with the need for upgrading so that structures can meet more stringent design requirements. The reasons why composites are increasingly used as strengthening materials of reinforced concrete elements may be summarized as follows: immunity to corrosion, low weight, easier application in confined space, reduction of labor costs, very high tensile strength, stiffness which may be tailored to the design requirements, large deformation capacity. Composites have disadvantages such as linear elastic behavior to failure without any significant yielding or plastic deformation, which lead to reduced ductility, high cost of the material, incompatible thermal expansion coefficient with concrete. Composites have found their way as strengthening materials of reinforced concrete elements such as beams, slabs, columns, where conventional strengthening techniques may be problematic. Composite material is a combination of two or more materials. Fiber-reinforced polymer composites are defined as a matrix of polymer material that is reinforced by fiber or other reinforcing material. In general terms, it could be said that the polymer is the glue that holds the composites and influences the physical properties of the composite and product, while the reinforcement provides the mechanical strength properties to the end product. The function of the matrix is to protect the fibers against abrasion or environmental corrosion, to bind the fibers together and to distribute the load. The metric has a strong influence on several mechanical properties of the composite, such as transfer modulus and strength, the shear properties, and the properties in compression. The metrics for a structural composite material can either be of thermosetting type or thermoplastic type. Epoxy resins, polyester, and vinyl ester are the most common matrix materials. They are thermosetting polymers with good processability and chemical resistance. Epoxies have in general better mechanical properties than polyester and vinyl ester and outstanding durability, whereas polyester and vinyl esters are cheaper. A high fiber aspect ratio permits very effective transfer of load via metric materials to the fibers. Fibers can be manufactured in continuous or discontinuous form. The fibers used for strengthening exhibit linear elastic behavior up to failure. There are mainly three types of fibers that are used for strengthening of civil engineering structure, namely glass, aramid, and carbon fibers. Physical and mechanical properties can vary a great for a given type of fiber. To summarize, the mechanical strength properties are dependent on the type, amount, and orientation of the reinforcement that is selected for the particular product. FRP materials consist of a large number of small, continuous, non-metallic fibers with advanced characteristics bundled in a resin matrix. Depending on the type of fiber, they are referred as aramid fiber-based, carbon-based fiber, or glass fiber-based reinforced polymers. Typically, the volume fraction of fibers in FRP equals about 50 to 70% for strips and about 25 to 35% for sheets. Due to the fact that the stiffness and the strength of the fiber is much larger than the stiffness and strength of the matrix, the properties of the FRP composite material are governed by the fiber properties and the cross-sectional area of the BF fibers. Reinforcing fibers contribute to the mechanical strength characteristic of the composite. The strength is dependent on the type, amount, orientation of the fiber surface treatment, and the compatibility of the fiber with the matrix polymer. By varying these parameters, a broad range of mechanical properties are possible. For example, a composite which has all the fibers aligned in one direction, it is stiff and strong in that direction, but in the transverse direction it will have a lower modulus and low strength. Also, the fiber volume fraction heavily depends on the method of manufacture. These same parameters allow the tailoring of the mechanical properties of the composite to the specific property requirements of the end product application. This is a major feature of the composite materials that allows their efficient use in a highly stressed application. The basic FRP strengthening technique involves the manual application of wet layup system by means of cold cure adhesive bonding. External reinforcement is bonded onto the concrete surface with the fibers as parallel as practically possible to the direction of principal tensile stress. Two different processes can be used to apply the fabrics. The fabric can be applied directly into the resin, which has been applied uniformly onto the concrete surface. The fabric can be impregnated with the resin in a machine and then applied wet to the sealed structure. Externally bonded FRP reinforcement is an efficient technique that relies on the composite action between a reinforced concrete element and externally bonded reinforcement. To guarantee the overall structural safety of the strengthened member, it is important that proper systems are used which depend on type of FRP, type of adhesive, method of curing, material preparation. The state of the repaired structure prior to the strengthening should be taken as a reference for the design of externally bonded FRP reinforcement. The design procedure should consist of a verification of both the serviceability limit state and the ultimate limit state. The following design situations have to be considered. Precedent situation corresponding to the normal use of structure, accidental situation corresponding to unforeseen loss of externally bonded FRP reinforcement, and special design consideration as fire resistance and impact resistance. It should be demonstrated that the strengthened structure performs adequately in normal use. To meet these requirements, the serviceability limit state verification concerns stresses have to be limited in order to prevent steel yielding, damage, or excessive creep of concrete and excessive creep or creep rupture of the FRP. Deformations, which may restrict normal use of the structure, induce damage to non-loading bearing members. Cracking, which may damage the durability, functionality of the structure, or which may endanger the integrity of the bond interface between FRP and concrete. The ultimate limit state, different failure modes that may occur have to be considered. In general, the failure modes can be subdivided to those assuming full composite action between the reinforced concrete member and the externally bonded reinforcements, and those verifying the different debonding mechanism that may occur. The failure modes of reinforced concrete elements strengthened with externally bonded FRP reinforcement may be divided into two classes. Those where full composite action of concrete and FRP is maintained until the concrete research crushing in compression or the FRP falls in tension. Those where composite action is lost prior to previous failure mode due to the peeling off of the FRP. In full composite action, we should consider Steel yielding followed by concrete crushing. The flexural strength may be reached with yielding of the tensile steel reinforcement followed by a crushing of the concrete in the compression zone, whereas the FRP is intact. Steel yielding followed by FRP fracture. For relatively low ratios of both steel and FRP, flexural failure may occur with yielding of the tensile steel reinforcement followed by the tensile fracture of the FRP. Concrete crushing. The relatively high reinforcement ratios failure of the reinforced concrete element may be caused by compressive crushing of the concrete before the steel yields. This mode is very brittle. Bond is necessary to transfer forces from the concrete into the FRP, as bond failure modes have to be taken into account properly. Bond failure in the case of externally bonded reinforcement implies the complete loss of composite action between the concrete and the FRP reinforcement and occurs at the interface between the externally bonded reinforcement and the concrete substrate. Bond failure may occur at different interfaces between the concrete and the FRP reinforcement. Debonding in the concrete near the surface or along a vacant layer. Debonding in the adhesive cohesion failure. As the tensile and shear strength of adhesive is higher than the tensile and shear strength of concrete, failure will occur in concrete. A thin layer of concrete will remain on the FRP reinforcement. Debonding may occur through the adhesive only if its strength drops below that of concrete. Debonding at the interface between concrete and adhesive or adhesive and FRP adhesion failure. Bond failures in the interface between concrete and adhesive or adhesive and FRP will only occur if there is insufficient surface preparation during the FRP application process because the cohesion strength of epoxy resin is lower than the adhesion strength. Debonding inside the FRP. This failure mechanism between fibers and resin may be explained by fracture mechanism. This might be case with high-strength concretes. Most failures of reinforced concrete members strengthened with FRP are caused by peeling off the externally bonded reinforcement. The weakness point in the bond between the externally bonded reinforcement and the concrete is in the concrete layer near the surface. Depending on the starting point of the debonding process, the following failure modes can be identified. Mode 1. Peeling off in an uncracked anchorage zone. The FRP may peel off in the anchorage zone as a result of bond shear fracture through the concrete. Mode 2. Peeling off caused at flexural cracks. Flexural cracks in the concrete may propagate horizontally and thus cause peeling off of the FRP in the regions far from the anchorage. Mode 3. Peeling off caused at shear cracks. Shear cracking in the concrete generally results in both horizontal and vertical opening, which may lead to FRP peeling off. In elements with sufficient internal shear reinforcement, the effect of vertical crack opening on peeling off is neglectable. And mode 4, peeling off caused by the roughness of the concrete surface. The roughness of the concrete surface may result in localized debonding of the FRP, which may propagate and cause peeling off. Composite materials are used for strengthening wood, masonry and concrete construction in order to increase the bearing capacity of construction under permanent and increased loads caused by earthquakes and environment. The externally bonded FRP reinforcement does not stop existing problems such as steel corrosion. Potential damage mechanism must be minimized and the concrete should be sound. If needed, the strengthening has to be preceded by concrete repair, the internal steel protection techniques. The following aspects should be considered. The minimum concrete tensile strength should be greater than 1.5 Newton on millimeter square if the damaged concrete has reached a depth that no longer allows shallow surface repair. Replacement of the concrete should be considered. Corrosion of the internal reinforcement should be stopped to avoid damage to the concrete due to expensive rust. Repair or protection is needed if the steel is already corroded or is likely to start corroding. Wide cracks may need sealing by means of injection. Any cracks wider than 0.2 millimeters should be injected by suitable, compatible low viscosity resin to fill and seal the cracks. To provide an adequate bond with the adhesive, the preparation of the concrete substrate should be carried out well. The substrate should be roughened and contamination-free in such a way that the concrete quality can be utilized in an optimum way. This is done by means of high-pressure blasting or grinding. Most of the wet layup systems require a smoother surface. Mechanical methods that may compromise the quality of the concrete should not be allowed. Regardless of the method, execution should not damage the concrete. The concrete should be sound and free from serious imperfections like steel corrosion, wide cracks, and potential damage mechanisms. The prepared surface should be dry and dust-free before application of the strengthening technique. The concrete surface shall be marked where the externally bonded FRP reinforcement has to be applied. Strips, laminates, or fabrics should be supplied to site at the specified width and cut to the necessary length as specified on the design drawings. They should be free from any contamination like oil, dust, carbon dust. For strips provided with an inbuilt peel ply, the ply should be removed immediately before application and the surface must not be touched by hand again. The strips should be handled with clean gloves and under dry conditions. They have to be verified for possible damage resulting from transportation, handling, and incorrect cutting. The application depends on the type of externally bonded FRP reinforcement. For strips and laminates, the adhesive ensures bonding only. For sheets and fabrics, the resin ensures both bonding and impregnation. The application of externally bonded FRP reinforcement is performed according to the specifications given by the manufacturer. The adhesive is applied as a thin layer to the concrete immediately after mixing. The adhesive is applied to the FRP sheet in a dome shape, having slightly more thickness along the center line of the plate. This reduces the risk of forming voids when the strip is applied. The strip is offered to the concrete surface, applying pressure by means of a rubber roller to ensure intimate contact with the concrete. The extra adhesive should be squeezed out along the sides. The final bond line should be of equal thickness along the strip. To achieve the required evenness of the concrete surface, it will specify to apply a primer. This shall be done in accordance with the specification given by the manufacturer. A low viscosity resin is applied to the concrete with sufficient thickness by means of roller brush. This process is known as undercoating. Then the sheet is applied by pressing it manually onto the adhesive in such way that it is stretched without introduction of voids. Impregnation and further pressing is performed by applying adhesive on top of the sheet with roller brush, and this process is known as overcoating. The final bond line should be of equal thickness along the sheet. Some form of finishing may be required for aesthetic purposes. in terms of fire protection, possible occurrence of damage, protection against UV radiation, a finishing layer can be crucial to the long-term integrity of the strengthened structure. Different types of finishing layers can be provided, such as painting, shot concrete, or fire protection panels. The compatibility between externally bonded reinforcement and the finishing layer should be provided. For specification concerning concrete repair technique and steel corrosion protection techniques, references is made to corresponding guidelines. Thank you for your attention.